roving reporter Noam here. For my science project, I'm going to interview a working scientist. Eanna Flanagan is a theoretical astrophysicist at Cornell University. Professor Flanagan graduated from University College Dublin in Ireland in 1987 and received his PhD in theoretical physics from Caltech in 1993, where he studied with Kip Thorne. By the way, Thorne is the guy who advised for the movie Interstellar. Professor Flanagan has been a member of the astronomy and physics departments at Cornell University since 1996. His research interests include cosmology, physics of neutron stars and black holes, quantum fields and curved spacetime, and studies of gravitational wave sources. By the end of this interview, I hope you all know what a gravity wave is, how it helps our modern understanding of gravity, and I hope you will have some idea of what curved spacetime is and why it is important. Tell me a little bit about yourself. How did you end up in this field? Did your interest in physics and the birth of the universe, which is what cosmology is, begin when you were little?
Yes. So, like many scientists when I was little, I read popular books about science and about what scientists have managed to figure out about the universe and how the universe began and how physics works. And it's been an exciting process of discovering steps and different generations making more and more discoveries. And so it's always been fascinating for me, and I've always wanted to be part of it. And I always liked mathematics as well when I was little, so it was always something I've always wanted to do.
So why did you switch from math to physics?
So when I was young, I studied both math and physics, and they're very closely related because you need to use math and physics. But eventually I decided when I was going to graduate school I wanted to study physics because it was about the real world. Parts of mathematics are relevant for physics, but parts are not. They're just things that we can explore, but they're not related to the real world. So I really wanted to understand how the real world works.
What is a gravity wave and why is it important?
So gravity, the normal gravity that you're familiar with, is a force, but Albert Einstein discovered that gravity can be understood in terms of space and time being curved. Just like a rubber sheet, if you imagine a stretched rubber sheet like a trampoline, and then you put a cannonball in the middle of the trampoline, it'll stretch and deform. So space is like that. It can stretch and deform in response to masses. And that's what gravity is, the curvature of space and also of time. That's what Albert Einstein discovered. And what gravity waves are oscillations in the curvature of space and time that travel along, that carry energy. Just like if you have a trampoline and you shake it at one end, you can make waves propagate right through the trampoline. And the reason that people are excited about gravity waves today is that we're on the brink of discovering gravitational waves. There are projects to try and detect them coming from space, and we hope to use gravitational waves as a kind of a tool to understand the universe and things in the universe like black holes in the early universe, just like we use X-rays and radio waves and different types of radiation to study the universe.
How would a passing gravity wave look or feel?
Well, you wouldn't be able to see it, and the problem with detecting gravitational waves is they're weak. So a very strong gravitational wave could be passing through us right now, and we never know because they don't influence us very much. They're very weak. The ones we try and detect are very weak. But if they were really, really strong, what we would feel is as if somebody was pulling you up through your head and down through your feet. So normally you feel like gravity is just pulling you along and pushes you all in one direction, but a gravity wave is a kind of gravity called tidal gravity that pulls part of you in one direction and part in the other direction. And it would feel like you were being pulled up at your head and down at your feet, and then a little while later you'd be squished down at your head and up at your feet, so it'd be oscillating back and forward. And that would be kind of a pushing and pulling, and you'd get tired of it pretty quickly if it was strong enough. If it was really strong enough, you could get pulled to pieces. A similar type of pulling and pushing happens if you fall inside a black hole. As you get closer and closer to the center of the black hole, you get pulled and squished more and more until you eventually get killed.
Oh.
The gravity waves are much weaker.
Okay. So if our sun just went supernova and we somehow had some protection against all that explosion stuff, would we be able to see the gravity waves?
Well, in principle, those gravity waves would be detectable. If the sun goes supernova, it's a pretty small fraction of the energy that goes into gravitational waves.
Okay. How fast do gravity waves move?
They travel at the speed of light.
Oh.
So.
Okay. So if our sun went supernova, would we be able to see the gravity waves right before we exploded?
Well, let's see. So the light signal would travel at the same speed as the gravitational wave signal. So from that point of view, you'd expect to see them both exactly the same time. But different parts of the explosion might happen at slightly different times. And so what happens in a supernova explosion is the inside of the star collapses, and that makes a shock wave, and then that comes out and blows off the outer layers of the star. Yeah. So the collapse and the bounce is what produces most of the gravitational waves, and that actually happens before the outer layers of the star get blown off. So we might see the gravitational waves a little first. So you'd have some warning.
Yeah. Do we need to worry about this supernova?
No. Only stars that are quite a bit heavier than our sun go supernova. When our sun gets very, very old in a few more billion years, it will gradually get dimmer and shrink down and turn into something called a white dwarf, which is a kind of an old dead star that's supported by a different kind of pressure, not just heat, which is our sun is being supported by heat, basically by heat.
So when that happens, it'll just be too cold?
Well, actually, before it becomes a white dwarf, it goes into this intermediate stage where it becomes something called a red giant, and it actually swells and gets bigger and bigger, and it actually extend out past the orbit of the Earth and vaporize the Earth.
Yeah,
so anyway. Hopefully we'll have colonized other planets before then.
How long do we have?
A few billion years. Yeah. So,
yeah,
the sun is pretty stable.
What is LIGO?
LIGO is a project. It's an instrument to detect gravitational waves that's being built, and it's a project with about 1,000 scientists involved, and it basically is a laser so it's an instrument containing two vacuum pipes, and they shoot a laser up and down the vacuum pipes, and it bounces off mirrors, and a gravitational wave comes along, moves the mirrors a little bit, and changes the property of the laser light, and then we can detect the gravitational wave. So it's a very, very sensitive instrument. On 9/11, when the Twin Towers collapsed, that cause and effect was able to be picked up by this instrument, even though the instrument was actually thousands of miles away.
That's pretty cool. So LIGO stands for?
It stands for Laser Interferometer Gravitational Wave Observatory, and it's been in operation for a few years. It was taken offline to be upgraded, and right now it's back running again, and they're just starting to search for gravitational waves again. It's not seen any gravitational waves yet, but hopefully in the next few years we'll see the first gravitational waves with LIGO.
Okay. When did you become involved with LIGO, and did you help build the original prototype instrument?
I did not help build the original prototype instrument, no. I became involved when I was a graduate student in the 1990s.
Yeah.
And my involvement with LIGO is I help a little bit on some of the design work for the inside of the pipe that holds the laser light. One of the things that can happen is the laser light can scatter and go where you don't want it to go. So I worked on systems to try and stop that from happening.
What sort of work do you do now? How are you involved with LIGO?
So right now, I'm not directly involved in the project, but I do work on calculations and theory for what LIGO might see. So one of the things that LIGO might see would be two black holes coming together in a big dramatic event that will make one big black hole. And so people all around the world are studying this type of process with computers and numerically and with calculations to try and understand it in more detail, because it's one of the main things that LIGO might see. So that's one of the things that I'm working on. Okay. Understanding what happens when one black hole eats another. It gobbles up the big black hole gobbles up the small one, and it gives off a lot of gravitational waves with some interesting patterns.
I'm just curious to know why do people want to know if gravitational waves are real? Like what would it do for us to have that information?
Well, so physics is kind of an empirical science. So our knowledge is based on observing and seeing, do our theories for what happens match with our observations. And right now our understanding of gravity it's fairly primitive in terms of the observational side, because we have this theory of gravity general relativity, and we have some observations that support it, but we don't have, we expect it to behave like the theory predicts, but we haven't actually directly detected it yet. So whenever we have a theory, we always like to check it out in all the different aspects to make sure that it's working properly, because sometimes we get surprised. Sometimes we think we understand something, we turn out not to. The history of science is full of discoveries where people thought they understood what was going on, but when you actually go and measure it, it turns out to be a little different. So it's always important to measure things whenever you can, just to make sure that Einstein was correct and that general relativity behaves as we expect it to.
So what could you do if you actually detected gravity waves?
Well, you would, first of all, check that general relativity was correct and our understanding was correct. But then after that, you can use it as a tool to understand the universe, to understand how many black holes are out there, how were they made, did they grow mostly by swallowing gas or swallowing little black holes? We can study things like neutron stars. They're exciting types of stars that are very small and very compact, and a lot of interesting things going on. And we can also hopefully study the very early universe with gravitational waves. So there, people try and detect gravitational waves indirectly using radiation left over from the Big Bang, not with LIGO. But that's another way where gravitational waves can tell us interesting things about the universe. So we kind of use gravitational waves as a tool, just like we use radio waves or X-rays in astronomy to measure interesting things.
If you could have anything you wanted from LIGO, what observation do you dream of, and what other observations from other detectors would you really like to see?
Well, let's see. From LIGO, I think the most exciting thing would be an observation that shows two neutron stars coming together and having a collapse to a big black hole, and that would give off a funny signal that sounds like a kind of a whistle, but then it gradually increases in frequency, and it gets louder and louder to the very end. And from it, you can measure properties of the neutron stars and see how far away they are and stuff like that. So that would be an exciting thing that LIGO could see, and it's one of the things it might see. What other observations? Yeah. Well, so there is another type of detector that instead of building it on the ground, you could build it up in space. And it would be sensitive to a different type of gravitational wave with a different frequency, just like radio waves are different from optical waves. They're both basically the same type of radiation, like magnetic radiation, but they're very different frequencies. So if you build an interferometer in space, you could detect gravitational waves of a different kind. And so there have been plans to build such an instrument, but it hasn't been built yet. So it would be exciting if one day we could do that. And potentially an instrument like that might be able to measure different types of gravitational waves. One of the most exciting types of gravitational waves would be waves from the very early universe that tell us about the very earliest few moments in the history of our universe.
So, what do you mean by when you say like different types of gravity waves? Are you just saying like where they came from?
I mean just basically different frequencies, like different colors of light.
Yeah.
And so they're basically the same thing, but they just have slightly different properties. And then with light, if you change the frequency enough, you can change it from visible light to radio waves or X-rays that are detected with very different kinds of instruments, even though they're fundamentally the same kind of radiation. It's the same with gravitational waves. If you change the frequency enough, it's fundamentally the same kind of object, but it's produced by different kinds of sources. You need to use a different technology to detect it. So it's really quite different.
Okay. Finally, what are some important questions for which gravitational wave observations could provide clues and insight?
Well, let's see. One important question is how the universe began. So the prevailing theory is that the very earliest moments of the history of the universe were a very rapid period of expansion called inflation, and gravitational waves could tell us about that, confirm it happened, and tell us at what energy scale it happened. So that's very exciting if we could do that. We could also learn about things like properties of matter when it's very, very dense. So matter is made up of atoms, and atoms have electrons going around the nucleus, and the nucleus is very, very dense. It contains protons and neutrons. And we've measured properties of the physics of nuclear matter, but we can only measure so much in our laboratories. And actually gravitational waves, by observing neutron stars, could tell us very interesting things about physics of nuclear matter that we can't detect in our laboratories. So that would be very exciting, directly connecting stuff that's going on in the universe millions of light years away to stuff on very small scales we try and probe in our laboratories, and they're directly linked. So that's another exciting thing that gravitational waves could hopefully do.
Oh, yeah. Thank you.
You're very welcome.
Yeah.